Welcome back. In the last half of this lecture, we're just going to carry out some examples of factoring polynomials completely. So for this polynomial that we have, f of x, again, if we're factoring it completely, we're going to need to first generate a list of possible rational zeros, and that'll be using our rational zero theorem. If we're thinking about the constant term, which happens to be positive 6, that could be factored in a variety of different ways. Factors are positive and negative 1, positive and negative 2, positive and negative 3, and positive and negative 6. For the leading coefficient, which is 2, the factors for that would be positive and negative 1 and positive and negative 2. And so that tells us then that for possible rational zeros, those would be anything of the form factor from the constant term over factor from the leading coefficient. So we have positive or negative 1, we have positive or negative 1/2, we have positive or negative 2 over 1, positive or negative 2 over 2, and then so on for all the rest. Now, one thing that's kind of nice here is that some of these are duplicates. So let me just get these all written down. And so there are some duplicates that we don't have to consider again. So for example, plus or minus 2 over 2, well, that's the same thing as plus or minus 1. And we already have plus or minus 1 on our list, so we don't really need it a second time. If you're thinking about plus or minus 6 over 2, that's the same thing as positive or negative 3, which we already have on our list, so we don't really need that again either. So if we eliminate the duplicates, we really have, for rational zeros, really we've got positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 6, there's a half, there's 3/2, and then that's it. So we have really only a limited list of values to check. Positive or negative 1, 2, 3, 6, 1/2, and 3/2. And of course, we're going to want to start with the easier ones first, with maybe the 1s, the 2s, the 3s, and then we'll deal with the harder ones afterwards if we have to. So let's start with, let's check, starting with 1. Is 1 a 0? And again, we do this by division. You could also check to see whether f of 1 is 0 or not. So I'll do 1, bringing down, multiplying, adding, multiplying, adding, multiplying, adding. That's not 0, so that means x minus 1 is not a factor. Okay, so let's do negative 1. This isn't super terrible. It's just can be time consuming just because there's no way to tell just by looking which one of the possible rational zeros is the right one, or if there is a right one. You just have to work your way through and methodically check each and every one, and hopefully you'll eventually hit on the right one. Now, you do have to be careful, of course, because it's very easy in the haste of multiplication to wind up making a mistake during synthetic division, or even just evaluating your function. So it's worth double checking the calculations that you do, the multiplying and adding and multiplying and adding and so on. So here I've got another remainder that is not 0. Remainder would be 12, so that tells me that x plus 1 is not a factor. So we've already crossed two things off of our list. If we're going back to our list of factors, we had possible factors were positive or negative 1, and we've now eliminated those, so that's gone. So I guess the next one up is to check positive or negative 2. So now let's do that next. So I'll do positive 2 first. So bringing down and multiplying and adding and multiplying and adding and multiplying and adding. And again, remainder's not 0, so that means x minus 2 is not a factor. We'll try negative 2. Bring down, and we multiply and add. Then we multiply and add, and we multiply and add. Okay, good. There we go. We have a remainder of 0, so that tells me that x plus 2 is a factor. And in particular, you can say that f of x factors as x plus 2 multiplied by this quotient. And that quotient would be 2x squared minus 7x plus 3. So we just need to now continue to factor, and I'll just add an extra page on in here to give myself some room. So we have that f of x was x plus 2 multiplied by 2x squared minus 7x plus 3. And now the next thing that we would want to do is continue on with factoring this. Now you've got two options, and I'm going to do maybe the easier option here. One option is you've now crossed off your list of possible zeros. You know 1 and negative 1 is, both of them are not zeros. You know that negative 2 was not a 0. Positive 2 rather was not a 0. Negative 2 was a 0. You could then continue to test the rest of these rational zeros if you felt like it. You could continue to test them in this polynomial to see whether or not any of those remaining zeros are zeros of this polynomial. But because it's a quadratic and we have ways to factor quadratics, then that's what I'll do on the side. So I'll just quickly on the side factor for myself 2x squared minus 7x plus 3. We'd be looking for numbers that multiply to 6 and add up to negative 7. That would be negative 6 and negative 1. And then we'll just factor by grouping. And so the polynomial that we have, that little quadratic, factors as 2x minus 1 times x minus 3. And I factored as far as I can go because here I've just got a bunch of linear factors multiplied together. Remember what I said was that for any polynomial, you should be able to factor it into linear factors and irreducible quadratics. And that's all we've got is a bunch of linear factors, so you can't factor any further, which means we are finished. All right. Let's do another one here. So if we're thinking about possible rational zeros, here, if we're thinking about the leading coefficient of 3, possible numbers that go into 3 are positive and negative 1 and positive and negative 3. For things that go into 6, we've got 1, 2, 3, and 6. And so if we're thinking about possible rational zeros, Remember that those rational zeros will be the constant terms factors over the leading coefficients factors. So we would have 1 over 1, 1 over 3, 2 over 1, 2 over 3, 3 over 1, 3 over 3, 6 over 1, and 6 over 3. And some of these are duplicates, of course. 3 over 3, that's the same thing as 1. We've already got 1 on our list, so we don't really need it. That's a duplicate. 6 over 3, that's the same thing as 2, and we've already got 2 on our list, so we don't really need that. So we have then that the only unique possible rational zeros, we've got positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 6, and then there would also be 1/3 and 2/3 positive and negative for possible rational zeros. Okay, so now I guess let's start checking. I'll start with maybe the nicest one, the easiest one, which is starting with 1. So I'll check whether 1 is a factor or not. 3, negative 10, 4, negative 4, 1, and 6. And so we'll do synthetic division, just multiplying and adding, and multiplying and adding. Oh, and there we go. That turned out really nicely. So that means that h of x will have x minus 1 as a factor. And that h of x then can factor out as x minus 1 times what's left over, which would be, that's constant, x, x squared, x cubed, x to the 4. So what's left over is a polynomial of degree 4. That would be 3x to the 4 minus 7x cubed minus 3x squared minus 7x minus 6. All right, and then we just need to continue along. And so what we will do next is check to see. Now, one thing that we might want to mention here is just because we found that x minus 1 was a zero, x minus 1 was a factor, doesn't mean that it can't be a repeated factor. So we found that 1 was a zero of our given polynomial, but 1 might also still be a zero of what's left over. So just because we've confirmed that 1 was a zero doesn't mean that we can stop checking it. It might be a repeated zero. It might have multiplicity more than 1. So that might be something that we'll want to do on the next slide. So let's do that. Let's check to see whether 1 is a zero of what's left over. So what's left over, let me just make sure I've got my coefficients correct. Coefficients are 3, negative 7, negative 3, negative 7, negative 6. So 3, negative 7, negative 3, negative 7, and negative 6. Let's get that. Try that again. 3, negative 7, negative 3, negative 7, and negative 6. There we go. And let's check to see whether 1 is a zero. Multiplying and adding. And the answer is no. So that means that we only have x minus 1 showing up as a factor once. That x minus 1 is not a factor of what's left over here. So that means we've done checking with x being 1. We'll need to check any other values of x. Check negative 1, check positive 2, negative 2, and so on. So let's continue checking. So the next one that was on our list to check was -1. Notice here I'm checking in my quotient. I'm not going back to my original function because we've already done some factoring for your original function. There's no need to go and see, does -1, is it a 0 of the original? If it's a 0 of the original, it'll be a 0 of the quotient as well. So now just continuing along, multiplying and adding, multiplying and adding, multiplying and adding, and unfortunately again we've come up with no -1 is not a 0, so too bad for that. Okay, continue along with 2. Multiplying and adding and multiplying and adding and multiplying and adding, and again, nope, it's not. And so sometimes, and this is why I wanted to do this example in particular, sometimes it may take multiple attempts to get to the point where you can factor and find 0. So here we've only so far crossed off the list 1, -1, and +2. We still have -2 and +3 to check, and then 6 and 1/3 and 2/3. So we're nowhere close to finished yet. Let's add some extra pages. Okay, so we've checked 1, -1, 2. Let's check -2 now. Bringing down and multiplying and adding and multiplying and adding and multiplying and adding and multiplying and adding, and nope, the remainder is not 0. So we've crossed positive and -2 off the list. I guess now let's move on to 3 and let's see what we get. Multiply and add, multiply and add, multiply and add, multiply and add. Oh yay, okay, so this turned out nicely. We have a remainder of 0, and so what we now know, h of x had, and I'm going to just scroll back here, h of x had x minus 1 as a factor, and then we had this quotient that was left over. So we still have x minus 1 as a factor, and the quotient that was left over, that was the thing that we were dividing into here, that has 3 as a 0. In other words, it has x minus 3 as a factor, and then what's left over, constant x, x squared, x cubed, we'll have what's left over is 3x cubed plus 2x squared plus 3x plus 2. Okay, so I'm going to pause here for just a second and just to say a couple of things about now moving forward. So if we wanted to now move forward here on factoring this polynomial further, we could continue along with what we've done so far. So we've now managed to cross off our list. We've looked at positive and -1. We've done that as much as we can. Same with positive and -2. We've shown that 3 was a 0. So we could continue and see, is 3 a repeated 0? Then check all the other ones as well to see if any of these happen to be zeros. But it's always a good idea to ask yourself, can you continue your factoring without needing to use the rational zero theorem? If you have a quadratic, you already know how to factor those. This isn't quadratic, it's degree 3, but hopefully, if I'm just lingering on this for a minute or two, hopefully you'll look at this and notice that it has an even number of terms, And it might be something where factoring by grouping could work. And in fact, it is something where factoring by grouping will work for you. So if I were to just write this out, I skipped a line here. If I were to just write this out, I could say that of the last factor there, you could factor by grouping, taking x squared out of the first two terms and taking positive 1 out of the next two terms. Which means that 3x plus 2 can be factored out of both of those, leaving x squared and plus 1. And you can check to see now on your list of possible rational zeros, the zeros that we have are 1, 3, and negative 2/3, and they were all on our list of possible rational zeros. X squared plus 1, that's an irreducible quadratic. That can't be factored any further. So now we've completed our work, and we factored as far as we can go. Now you could, again, I could say if you wanted to, you could continue checking to see one factor at a time with what's left over. But you would have to go quite a ways down the list of possible rational zeros before you get to testing the negative 2/3. So if you can factor an easier way using some other technique, that's something I would recommend doing instead. So we factored h of x. Let's give a shot to one more. Here, this is the example of finding all the intercepts for the graph of this function. And so one intercept we can find right away. We can say what the y-intercept is. Because remember, for a polynomial, the y-intercept has the y-coordinate of whatever the constant term is. And the constant term is 4. So that means that my y-intercept should be 0, 4. And then for the x-intercepts, that's the same thing as finding the zeros. So for the x-intercepts, we're going to need to think about factoring this. And so this is where we're going to need to think about using the rational zero theorem. I'm looking at my leading coefficient and looking at my constant term and looking at the factors of those numbers. And so that's telling me that my possible rational zeros could be positive or negative 1 over 1, positive or negative 1 over 2, positive or negative 1 over 3, positive or negative 1 over 6, and then the same thing with 2 over 1, 2 over 2, 2 over 3, 2 over 6, and 4 over 1, 4 over 2, 4 over 3, and 4 over 6. And a lot of these are duplicates, so there is quite a few that we can actually eliminate. 2 over 2, that's the same thing as plus or minus 1, so we don't need that again. Plus or minus 4 over 2, that's the same thing as 2 over 1, which we already have, so we don't need that. Plus or minus 4/6, that's the same thing as plus or minus 2/3, which we already have, so we don't need that as well. And it looks like I said 2/6, but I wrote down 2/3 here. Now let me just fix that. There we go. So sometimes I say something and I write something completely different down. The other one that we might want to cross out then is this, the plus or minus 2/6, because that's the same thing as plus or minus 1/3, which we, again, already have. When we're looking at the rational zero theorem, remember that it's just telling you here's the long list of all the possible rational zeros, and there are sometimes duplicates in the list. So in this case, we had 1 and 2 over 2 that were duplicates. We have 1/3 and 2/6 that were duplicates. We have 2 and 4 that were 2 and 4 over 2 that were duplicates. And we have 2/3 and 4/6 that were duplicates. So again, I've gone through my list and I've gotten rid of any duplicates. So really, the long list of rational zeros is we have plus or minus 1, 2, 4, a half, a third, a sixth, 2/3, and 4/3. So that's my long list of possible rational zeros. And then all I need to do is then go through my list and find any rational zeros that I can find and see who's a rational zero and who's not. And then once I have, then I can use that to factor. All right, so let's get started by starting with 1 and -1 and 2 and -2 and all the rest. So we had, for our polynomial, it was 6x cubed minus 23x squared minus 5x plus 4. So my coefficients are 6, -23, -5, and 4. And so I'll start with checking 1. And so basically all we're doing here is we are just going to be doing the same process of multiplying and adding. And if our remainder is not 0, then we can move on to the next. So 1 is not a 0. Let's try -1. Multiplying and adding, multiplying and adding, multiplying and adding. Nope. Okay, so positive or -1, that didn't work. Let's try +2. And we multiply. There we go. And we add. We multiply. We add. We multiply. We add. And that's not 0, so okay, we'll continue onward. Let's try -2. So we multiply, and then we add. We multiply, and then we add, and then we multiply. Ooh, I don't know if I'll be able to fit this in. There we go, sort of. And then we add. And that's not 0, so there we go. So far we've eliminated from our list, if we're looking back at our list of possible rational zeros, we've eliminated positive or -1 and positive or -2. Neither of them happen to be zeros, so that means there's no x-intercepts at 1 or at 2. So I guess next one to check is 4. And then we'll just do the usual, multiplying and adding and multiplying and adding and multiplying and adding. And there we go. We've got a remainder of 0. And so that means we've got our quotient of 6x squared plus x minus 1. And that x minus 4 must be a factor. So that means that for our polynomial that we started with, which is g of x, this cubic polynomial, we can now say that g of x is factored as, let me just add an extra page. So g of x is factored as x minus 4 times what's left over, and what's left over was 6x squared minus x, or sorry, 6x squared plus x minus 1. And then the only thing left for us to do would be to continue to factor. Just double checking, 6x squared plus x minus 1. Yes, good, awesome. The only thing left for us to do would be to continue factoring. You could use, again, the rational zero theorem if you wanted to. If you're thinking about what are possible rational zeros here, it would be positive or negative 1 over 1, 2, 3, or 6. You've already checked 1 over 1, so we don't need to check that again. The only possible rational zeros left to check would be 1/2, 1/3, and 1/4, both positive and negative. But I don't think you really need to do things that way. Again, if you can factor in an easier way, feel free to factor. So if you were to factor this quadratic same way that we've factored so many others, I'm going to just skip over this step. I'll leave that for you to do as an exercise. But you can confirm that this does factor as 2x plus 1 times 3x minus 1. That if you were to factor in the same way that I factored over here, the same way that I factored this quadratic, using that same technique, you'd be able to factor the quadratic that we have left over to give us this. And so now for x-intercepts, we can say, well, the zeros are x equals 4, x equals negative 1/2, and x equals positive 1/3. If we were to let each of these be equal to 0, that's what we would find. So that means that for our x-intercepts, we have intercepts at 4, 0, negative 1/2, 0, and 1/3, 0. Okay, and now for our last example, we want to sketch the graph of this function. And so we'll need to find a bunch of things. First off, we'll want to find our intercepts. And one intercept we can find right away, that would be our y-intercept. And that would have to be at 0, negative 18. Remember, for a polynomial, that the constant term, that's the y-coordinate for the y-intercept. For the x-coordinates, we'll need to find the zeros for this polynomial, and so for that, we'll use the rational zero theorem. Leading coefficient is 1, factors are plus or minus 1, constant term is negative 18, factors are plus or minus 1, 2, 3, 6, 9, and 18. And so that means that possible rational zeros could be any of these numbers over 1, which of course means that it's really just plus or minus 1 over 1, 2 over 1, 3 over 1, 6, 9, or 18 over 1. One thing we also know here, before we get into the finding of these zeros, is that since this is a fifth degree polynomial, there will be at most 5 possible factors. So that means although we've got 2, 4, 6, 8, 10, 12 different numbers that we could theoretically check, we know that all of them will not be zeros. At most 5 of them could be zeros, and potentially maybe even less of them. So we'll start by checking with the easiest ones, 1 and negative 1, then move our way up to 2 and negative 2, 3 and negative 3, and then hopefully we won't have to get all the way down to these very last ones. But if we do, then so be it. So we'll start off with whether 1 is a 0 for our given polynomial. And we just do our synthetic division, bringing down, multiplying, and adding, multiplying and adding, multiplying and adding, multiply and add, multiply and add. And we have that our remainder is 0. So that tells us that yes, indeed, we do know now that f of x can be factored as x minus 1 times what's left over, which is constant x squared, x cubed, x to the 4. So in other words, what's left over would be x to the 4, 3x cubed, 7x squared, 15x, and 18. There we go. And so the only thing that we would need to do now is just to check to see, well, what else is a factor of this? Now, when we're looking at the what's left over, even though we found that x minus 1 was a factor for our polynomial f of x, x minus 1 might also still be a factor of what's left over. So what we're going to do is, even though we found that 1 was a 0, we should check to see whether 1 is a repeated 0. Maybe it's a 0 of what's left over. So let's check to see if we were to take what's left over, 1x to the 4, 3x cubed minus 7x squared minus 15x plus 18. And if we were to do synthetic division, bringing down, multiplying, adding, multiplying, adding, multiplying, adding, multiplying, and adding, we can see that yes, we do have that 1 is a 0 that's repeated. It's repeated twice. So what we can say now then is that f of x has x minus 1 squared as a factor, and what's left over is this quotient. Constant term x squared, x cubed. So what's left over is x cubed, 4x squared, minus 3x minus 18. So let's just double check that we got our coefficients correct. 1, 4 minus 3 minus 18. Let's check to see. 1, 4 minus 3 minus 18. Good, we've got those correct. And so now that we've checked and we found that 1 was a 0 twice, we want to check and see, is 1 a 0 a third time? You never know. Something might be a 0 multiple times. So let's see if we can get one more 0 out of this. Bringing down, multiplying, adding, multiplying, adding, multiplying, adding, and the answer is no. So it looks like x minus 1 squared, that's the highest power I'm going to get for that x minus 1. Okay, well, if positive 1 isn't another 0, we can check negative 1. And let's see, negative 1, if we were to look at that, bring down, multiply, add, multiply, add, multiply, add. Nope. Okay, so we've excluded two things now. So I'm just going to go back and say, for our rational zeros, we've already exhausted the 1 and the negative 1. We don't need to check those anymore. We've taken out all of the x minus 1s that we can, and we also know that x plus 1 is not a factor. So I guess we'll move on to the next and check to see, what about 2? So now we'll continue to work with 2. Okay, so I'll bring down, I'll multiply, I'll add, I'll multiply, I'll add, I'll multiply, and I will add. Oh, there we go. That turns out nicely. So it turns out to be that x minus 2 is a factor. And so that means that f of x, we had x minus 1 squared. we've now got x minus 2, and what's left over would be x squared plus 6x plus 9. And that factors nicely. If you're looking for numbers that multiply to 9 and add to 6, it's 3 and 3. So actually, this factors out as x minus 1 squared, x minus 2, and x plus 3 squared. Okay, so we've got almost everything that we need. So let's just finish off getting our ideas here together. We've got, if we're zooming back to the beginning, we have our our y-intercept, 0, negative 18. And now we've factored things as much as possible, and so from that we can now find our x-intercepts. We know what our zeros are. We have zeros of 1 and of 2 and of negative 3. And we've got our multiplicities here as well. So we know that x being 1 has a multiplicity of 2. That x being 2 has a multiplicity of 1. Notice that the power on x minus 2 is just 1. And for the last one, we've got x plus 3. The 0 is negative 3, and x plus 3 was squared, so the multiplicity is 2. And so if we're now talking about behavior at the x-axis, at 1, we'll touch the x-axis. At 2, we'll cross the x-axis. And at negative 3, we will touch the x-axis. And again, reminder from back in the previous section that wherever the multiplicity is odd, that's where we'll cross the x-axis. Whenever the multiplicity is even, that's where we touch, but don't cross the x-axis. And the only last thing left for us to do is to talk about end behavior. And so for this, we need to go back to the beginning of things and look at our polynomial as it was originally given. And look at that leading term. And the leading term for this polynomial was x to the power of 5. So now if we're going to talk about end behavior, this should be the same end behavior that x to the power of 5 has. And remember, the graph for x to the power of 5 looks pretty much the same as the graph for x cubed. So that means that for our graph, we should have that this polynomial goes up to positive infinity on the far right and goes down to negative infinity on the far left. So now we'll put all of our clues together, and I'll start with the zeros, our 1, 2, and negative 3. So let's put those in. We have zeros of 1, 2, and negative 3. We also had our y-intercept of negative 18. So I'm going to need to label that. That's not at a tick mark, so I will need to label that one. The other x-coordinates, I won't need to label them. And then now we'll start to put things in, beginning with our end behavior. Our end behavior happens after our last x-intercept and before the first one. So before the first x-intercept on the far left, we are heading downward. And after the last x-intercept in the far right, we are heading upward. And that's what we have back here in our end behavior. At the far right, we go up, and at the far left, we go down. Now we go back and remind ourselves what's going on with our zeros. At our zeros, at 2, we're going to cross the x-axis, but for the others, we're going to touch at the x-axis. So that means at negative 3, we were supposed to touch the x-axis and then go back the way we came. We're going to have to make our way to that y-intercept, so I've done that. And I'm going to have to make my way to that x-intercept. There we go. At 1, I'm supposed to touch. And I have to make my way back. So there we go. I've made my way back. And at 2, I'm supposed to cross. So this is my sketch of what my polynomial looks like, what my function f of x looks like, which in factored form. Here I'm just going to label that. That was x minus 1 squared, x minus 2, x plus 3 squared. You can label it with either the factored version or the unfactored version, either way. A couple of things, though, that we can't really tell based on our graph and based on our skills yet with graphing polynomials. We know that there is a turning point somewhere between 1 and 2, because we know at 1 we touch the x-axis, then we have to make our way back to the x-axis for 2. So at some point we go down and then go up. We don't know how far down it is. Maybe it's a little bit, maybe it's severely, but unfortunately we don't have the skills to be able to tell how far down it goes. So this is my sketch of it. I've shown it only going slightly down, but I really don't know. That's why I haven't bothered to label anything here. I haven't tried to find out what the turning point is, because again, you don't know exactly where the turning point is. It doesn't have to be exactly in the middle. It might be maybe it turns very early. Maybe that's the sort of shape that it has, or maybe it goes down and then very late on it turns back up. So I have no idea exactly where the turning point is based on what we can do in this course, so this is as best as I can do. I do know that between 1 and -3, it has to go down to at least -18. Maybe it goes down further. This, again, I don't really know, and that's not something that I can tell with the skills that we've got from just pre-calculus. So this is not a graph in the sense that we've got all the features of this function visible in this picture. There is still a little bit of uncertainty. I don't know whether -18 is a relative minimum or not. My graph makes it look like it's a relative minimum, but it's also possible that this graph might be that we make our way through the y-axis and then keep going down for a little while further before coming back up. That's also a possibility, and that's something that unfortunately we won't be able to tell based on our graph.